Welcome to the Bodhi Academy. My name is Amisha Palasso, and in today's video we will continue with the chapter Electrochemistry class 12 chapter 2. So now let's understand what does conductivity mean. So specific conductivity of conductivity of an electrolytic solution at any given concentration is the conductance of unit volume of a solution kept between the two platinum electrodes with a unit area of cross section and at a distance of unit length. The conductivity decreases with decrease in concentration as the number of ions per unit volume that carry the concentration in a solution decrease on dilution. So basically, to understand this, last class we discussed what is conductivity. Conductivity is the ability to conduct. Now conductivity, it is directly proportional to the concentration of any solution that is given. So if the concentration of the solution is increasing, the conductivity will increasing. So basically what happens is that when we say concentration of the solution, we are trying to talk about a number of ions that are present. Number of concentration, the amount of concentration increases in 10 increases the number of ions that are present in the solution. So if the number of ions are increasing in the solution, therefore there are more current carriers that are produced. So therefore more of current is going to be passed throughout a solution. Therefore what we can say is that the conductivity increases with increase in concentration, that is the number of electrons that are present per unit volume. Now if we talk about molar conductivity. Molar conductivity of a solution at a given concentration is the conductance of a volume V of a solution containing 1 mole of electrolyte that is kept between the two electrodes with the area of cross section A and a distance of unit length. Now molar conductivity and conductivity are actually the same terms, only that conductivity and molar conductivity are inversely related to each other. It is basically the same amount, that is the given concentration is the conductance of volume V of a solution containing mole. So in this case we only talk about 1 mole of electrolyte when it is present in the given solution. So now if we talk about molar conductivity, what we can say is that molar conductivity will decrease with increase in the concentration. Okay, so what happens is that if we try to understand it in simple words, say I have a container which has say 4 small beads particles which are present, okay, and the volume is into that same solution say is 50 ml. Okay, now what I am doing, when we say conductivity, we talk in terms of number of ions that are present per unit volume. Okay, so number of ions here are say 4, okay, and unit volume is say 50 ml. Okay, now what I am doing is that I am increasing the volume. Say now I have made a volume to 100 ml. So initially it was 4 upon 50. So initially what it was 4 upon 50 ml. Okay, so initially it was 4 upon 50. Now I have changed the ratio to 4 upon 100. Okay, so now the ratio has changed. So what will happen? Will the conductivity remain the same? In this case the conductivity will vary. So this is what we are talking about. So when we talk in terms of conductivity or specific conductance, we say that it increases with increase in concentration. Okay, but whereas when we talk about molar conductivity decreases with increase in concentration or increases with decrease in the concentration. So molar conductivity, it is given by K upon C, where K is the conductivity and C is the concentration. So C is the concentration in moles per volume, K is the specific conductivity, and M is the molar conductivity. So as the solution contains 1 mole of electrolyte, the above equation can be written as M equals to K into V. Now molar conductivity increases with decrease in concentration as the total volume V of a solution that contains 1 mole of electrolyte also increases. Upon dilution, concentration decreases when the concentration approaches 0. So now when we talk in terms of dilution. So when we say dilution, what we can say is we are talking about more of molar conductivity. In that case, what we are doing, we are diluting the solution more and more. So therefore, if we add more of more volume, what will happen? So concentration is going to be the same, okay, but the molar conductivity is in turn going to differ. Now when the concentration approaches 0, the molar conductivity of the solution is known as limiting molar conductivity. That is given by lambda naught m or E naught m. So variation of molar conductivity with concentration differs for now strong and weak electrolytes. So basically what we know about strong electrolytes is that they are easily dissociating. They can easily break down into their constituent cations and anions. Weak electrolytes, they do dissociate, but they dissociate very slowly, okay. Now variation of molar conductivity with concentration for strong electrolytes. For strong electrolytes, the molar conductivity, it increases slowly with dilution. So what they are saying, if we have strong electrolytes that are present in the solution, then the molar conductivity, it will increase with the dilution. So what we are doing, we are increasing the, when we say dilution, what does it mean? That we are increasing the volume of the solution. So the plot between the molar conductivity and C, that is concentration raised to half, concentration raised to half, so this is raised to half, okay, raised to half is a straight line graph having an intercept equal to lambda naught m. Lambda naught m is the molar limiting molar conductivity. The value of limiting molar conductivity, that is lambda naught m, can be determined from the graph or with the help of kohlrausch's law. Now what is this kohlrausch's law? So kohlrausch's law of independent migration of ions, it states that the limiting molar conductivity of any electrolyte can be represented as the sum of the individual contributions of the cations and the anions of the electrolyte. Now say when we are stating about the limiting molar conductivity of any electrolyte, that can be represented as the sum, the total of the number of cations and the number of anions that are present in the given electrolyte. So for strong electrolytes, the molar conductivity, it increases slowly with dilution. The plot between the molar conductivity, and therefore it is a straight line graph. Now so m will be equal to lambda naught m. A is the constant that is equal to the slope of the line. So A is the slope and C is the concentration raised to half. Now with respect to with concentration of weak electrolytes. So for weak electrolytes, the graph plotted between molar conductivity and concentration, where C is the concentration, is not a straight line. So we are not going to get a straight line in terms of weak electrolytes. Weak electrolytes have lower molar conductivities and they have lower degree of dissociation at higher concentration, with increase steeply at lower concentration. Therefore, limiting molar conductivity, that is lambda naught m, cannot be obtained by the extrapolation of molar conductivity to zero concentration. So in this case, what we are saying is that we cannot obtain lambda naught m by just extrapolating it onto the y-axis. Hence here what we have to use the kohlrausch's law of independent migration of ions to determine limiting molar conductivity. So for strong electrolytes, we were easily able to draw extended line to the y-axis and we were able to get the limiting molar conductivity. But when it comes to weak electrolytes, we cannot do so because they have very low molar conductivities and their degree of dissociation is even lower. So in this case, what we have to do is we use the kohlrausch's law of independent migration of ions. So what does that say? That the limiting molar conductivity can be given as the sum of the total number of cations and the anions that are present in the electrolyte. Now, this application of kohlrausch's law. So using kohlrausch's law of independent migration of ions, it is possible to calculate firstly limiting molar conductivity for any electrolyte from the lambda of individual ions. So lambda of individual ions if we have, we can find the limiting molar conductivity. Moreover, for weak electrolytes like acetic acid, it is possible to determine the value of its dissociation constant once we know the limiting molar conductivity and lambda m at a given concentration C. So using kohlrausch's law, application is first is finding limiting molar conductivity if we know lambda m, and second is use for weak electrolytes we can find their dissociation constant if we know limiting molar conductivity and lambda m at any given concentration C. So now that was about variation of conductivity and molar conductivity with concentration. Now next we will look at the electrolytic cells and electrolysis. Now in an electrolytic cell, the external source of voltage is used to bring about a chemical reaction. Now in an electrolytic cell, what we are saying is that we use some external source, correct? So we are providing the electricity and then the chemical reaction occurs. In electrochemical cells, what was happening? The chemical reaction was occurring first and that was in turn generating electricity. So the electrochemical processes are of great importance in the laboratory and the chemical industry. One of the simplest electrolytic cell consists of two copper strips that are dipped in an aqueous solution of copper sulfate. So here what they are doing is they apply a DC voltage to the two electrodes. Then what happens? The Cu2 plus ions which are there, they discharge at the cathode, that is the negatively charged, and the following reactions occur. So Cu2 plus is giving out 2 electrons. It is taking up 2 electrons and it is going in zero oxidation state. So copper metal is deposited on the cathode, and at the anode copper is getting converted to Cu2 plus ions by the reaction Cu2 plus 2 electrons. So here at the anode what is happening? Copper is giving its 2 electrons and it is going in this ion state. Now thus copper is dissolved as in it is oxidized at the anode and deposited, that is reduced at the cathode. So this is the basics for any industrial process in which impure copper is converted to copper of very high purity. So the impure copper is made an anode that dissolves on passing current, and pure copper is deposited at the cathode. Many metals like sodium, magnesium, aluminum, etc., they are also produced on large scale by this electrochemical reduction of their respective cations, where no suitable chemical reducing agents are available for this process. So sodium and magnesium metals, they are produced by electrolysis of their fused chlorides, and aluminum is produced by electrolysis of aluminum oxide in the presence of cyrolite. So what they are saying is that sodium and magnesium, these both are produced by electrolysis. Sodium is produced by sodium like NaCl, so they are fused with their chlorides, and for aluminum is produced by electrolysis of the aluminum oxide itself, and they use this catalyst known as cyrolite. Now quantitative aspects of electrolysis. So Michael Faraday was the first scientist who described the quantitative aspects of electrolysis. Now Faraday's laws also flow from what has been discussed earlier. So now what we will see is we will talk about the laws that are given, laws of electrolysis that are given by Michael Faraday. So after his extensive investigation on electrolysis of solution and melts of electrolytes, Faraday published his results during 1833-34 in the form of following well-known Faraday's two laws of electrolysis. So the first law, what does the first law tells us? So the first law tells us that the amount of chemical reaction which occurs at any electrode, okay, the amount of chemical reaction that occurs at any electrode during electrolysis by current is directly proportional to the quantity of electricity that is passed through the electrolyte. So what are we saying? That the amount of chemical reaction that occurs at any electrode, may it be the cathode or may it be the anode, okay, during electrolysis, that is directly proportional to how much of current is being supplied through the electrolyte. The second law says that the amount of different substances that are liberated by the same quantity of electricity passed through the electrolytic solution, they are proportional to the chemical equivalent weight. So what they are saying is that the amounts of different substances, as in the byproducts that are produced during the produced during when electricity is passed through the given electrolytic solution, that amount it is directly proportional to the chemical equivalent weights. Now when we say chemical equivalent weights, it means that when the atomic mass of the metal is divided by the number of electrons that are required to reduce the cation. So if we say atomic mass of metal, say if we talk about sodium, so it was 11, and how much electrons are required to reduce the cation, and we have sodium, we know it is Na plus, only 1, so it will be 11 upon 1. So that is the amount of different substances that are liberated. There were no constant current sources available during Faraday's time, so the general practice was to put a coulometer, a standard electrolytic cell, for determining the quantity of electricity that is passed from the amount of metal deposited or consumed. However, coulometers are now absolute, and we have constant current. So back then there was no source of constant current, so in that case they used to use this a standard electrolytic cell which used to give in the electricity supply. Now whereas we have a flow of constant current that is happening, so in that case we can say that the sources available and the quantity of electricity, that is Q, is passed by Q equals to IT, where Q is the quantity of electricity that is given in coulombs, and I is the current that is in amperes, and T is the time in seconds. So now the amount of electricity or charge required for oxidation or reduction depends on the stoichiometry of the electrode reaction. Now for example, Ag plus electron giving Ag. Here the stoichiometry is 1. So we can say that it is 1 mole of electron is present for the reduction of 1 mole of silver ion. So we know that the charge on 1 electron is 1.6021 into 10 raised to minus 90 coulomb, correct? Now if you have to find, therefore the charge on the 1 mole of electrons will be equal to how much? 1 mole has how many number of molecules, that is Na, that is Avogadro's number. So that if you multiply it with the charge of 1 electron, we will be able to get the quantity of electricity, and this quantity of electricity is known as the Faraday's constant, and it is represented by the symbol F, and it has a value of 96487 coulomb mole inverse. Now for approximate calculations, we use 1 Faraday equals to 96500 coulombs mole inverse. For the electrode reactions of magnesium, that is having 2 electrodes, and aluminium having 3 electrodes, it is obvious that this 1 mole of Mg2 plus and Al3 plus require 2 moles of electron. So in this case the value is going to change. So in commercial production of metals, current as high as 50,000 amperes are used, that amounts to about 0.518 Faraday per second. Now let's talk about the different products of electrolysis. So products of electrolysis, it depends on the nature of the material that is being electrolyzed, and the type of electrolytes being used. So electrolysis, product of electrolysis mainly depends on 2 things. One is the material that is being electrolyzed, and second is the type of electrodes that are being used. Now if the electrode is inert as in non-reactive, so example would be platinum and gold. In this case they don't participate in the chemical reaction, and it only acts as a source or sink for electrodes. On the other hand, if the electrode is reactive, in that case it will tend to participate in the electrode reaction. Thus the product of electrolysis may be different for reactive and for inert electrodes. So the product of electrolysis, it mainly depends on different oxidizing and reducing species present in the electrolytic cell and their standard electrode potential. Moreover, some of the electrochemical processes, though feasible, are so slow kinetically that at lower voltages this do not seem to take place, and therefore we have to take extra potential has to be applied, which makes such a process even more difficult. So what we are saying now is that some of the electrochemical processes, they are not feasible, okay? They are kinetically so slow, and they require such low voltages. In that case they do not tend to occur. So in that case we have to supply it with some extra potential that is known as the over potential, and that due to this extra potential that is being applied, these processes, the occurrence of such processes becomes very much difficult. Now for example, if you use molten NaCl, the products of electrolysis are sodium, that is Na plus metal, will get NCl2 gas. Here we have only one cation, that is Na plus, which is reduced at the cathode. So Na plus electron will give us Na, and one anion, that is Cl minus, which is oxidized at the anode. So Cl minus will give us half Cl2 plus 1 electron. During the electrolysis of aqueous sodium chloride solution, the products are what? NaOH, Cl2 and H2. In this case, besides Na plus and Cl minus ions, we also have what? H plus and OH minus ions along with the solvent molecules of H2. So at the cathode there is a competition that is happening between the reduction reaction. So we have Na plus that is going to Na, and we have H plus that is going to H2. So now if you see the values, they are E0 cell values, what we see is that the reaction with higher value of E0 value is preferred, and therefore the reaction at cathode during electrolysis is E0. So when we have two values of E0, we always prefer the one which is high. So if we consider minus 2.71 and 0.00, obviously 0.00 is a higher value. So therefore at the cathode, which reaction is taking place? This H plus electron giving half of H2. But H plus aqueous is produced by the dissociation of what? H2. So H2O on dissociation gives us H plus OH minus. Therefore, now the net reaction will be what? H2O plus electron giving us half H2. Along with that we will also get OH minus. At the anode, the following reduction oxidation reactions are possible. So we have Cl minus breaking down into Cl2, and we have H2O getting dissociated into H plus and O2. So here also we have to look at the higher value. So the reaction at anode with a lower value here is preferred, therefore water should get oxidized in presence of Cl minus. However, on account of over potential of oxygen, reaction 2.36, so this one is preferred. Thus, the net reactions may be summarized as so. So, NaCl in presence of water, it will dissociate into Na plus and Cl minus. At cathode, what will happen? H2O, which is there, it will give out one electron and it will go into H2 plus, that is gaseous, and OH minus ions in the aqueous solution. Anode, what we will have? We will have Cl minus ions, which will take up electrons and they will go into Cl2 gaseous state. So the net reaction will be NaCl plus H2O giving us Na plus, OH minus, half H2 plus half Cl2. So the standard electrode potential are replaced by the electrode potential given by the Nernst equation. To take into account the concentration effects during the electrolysis of sulfuric acid, the following processes are possible at the anode. So what you are saying is that now the standard electrode potential, that is E0, is now replaced by the electrode potential, that is E cell, that is given by in the Nernst equation. So in that case, what we are taking accountability for even the concentration of these ions. So if you have 2 H2O, it will go into O2 plus H plus and 4 electrons. In that case, standard electrode potential is 1.23. If we have sulfuric acid, for dilute sulfuric acid reaction 2.38 is preferred, but at higher concentration of H2SO4 reaction 2.39 is preferred. So what is happening when the concentration is low? In that case we prefer this reaction. When the concentration is higher of H2SO4, in that case this reaction is preferred, which has a higher E0 cell value. Okay. So that was it for this part of the chapter. I hope you have understood. In the next class, we will talk about the applications, that is the batteries. So thank you so much for watching today's video. Please don't forget to like, share and subscribe to the Bodhi Academy.